Good evening, students. Welcome to day 4 POC-II crash course. So happy new year 2026. So I hope in yesterday's class, I told you people to write your new year resolutions. I hope you might have written those new year resolutions. If not, soon after this particular class, make a list of new year, that is 2026 year resolutions, and make a plan how to execute those resolutions and get the success in 2026. So in last 3 classes, I have covered some of the most important topics from Unit 1, that is aromatic hydrocarbons. And I have also discussed in yesterday's class some of the university examination questions and also some of the model GPAT questions, which are from the theory of orientation and reactivity in monosubstituted benzene. Okay. So if you have missed yesterday's session, you can watch replays. All the earlier 3 days replays will be available on my YouTube channel. And in today's session, I'll be discussing about Unit 2, Chemistry of Phenols. So again, today also, I'll be discussing about some of the most important topics. So stay with me till the end of this particular live session, because at the end of this particular live session, I will show some of the important questions and how to answer those questions when it comes to examinations. Okay, so all those small tips I'll be giving you at the end of this particular live session. So stay with me till the end of this live session. So I hope today also you're ready with your pen and notebook and water bottle. Now let's get into the topic. Phenols are usually expressed by the general formula AROH. So this is the structure of phenol. So here AR can be a phenyl ring system as shown here, or it can be a substituted phenyl moiety also. That means this phenyl ring system may have some substitution XYZ. That means it can have additionally amino group, methyl group, and so on. In phenols, this aromatic ring system can be even replaced with some of the polynuclear aromatic hydrocarbon systems, such as naphthyl ring system and so on. Both alcohols and phenols, they share a common functional group, that is OH group, that is hydroxyl group. But the difference is here, in case of alcohols, the hydroxyl group is attached to an aliphatic carbon. Let us consider an example. So ethanol is an example for aliphatic alcohol. Here hydroxyl group is attached to a open chain carbon system. In case of phenols, hydroxyl group is attached to an aromatic carbon. It can be a phenyl ring or it can be naphthyl ring. Even though functional group wise it is similar, that is having same OH group, but because it is attached to two different types of carbon environment, their properties are entirely different. Both alcohols and phenols, they undergo Williamson synthesis to give corresponding esters. In case of phenols, the hydroxyl group is attached to either aromatic ring system or polynuclear aromatic ring system. Thus, phenols are considered to be aromatic compounds. As you are aware that the properties of aromatic compounds are entirely different from that of aliphatic compounds. It is because of this reason, even the phenols are having same hydroxyl group as that of alcohols, yet they exhibit different properties when compared with alcohols. Now that you have understood what are phenols, now let us move to the next topic, that is methods of preparation of phenols. Again, there are several methods of preparation you will find in the literature, that is in your reference books and textbooks, okay? But here I am giving only few important methods of preparation so that you can easily prepare, remember, and you can produce the same thing when it comes to the examinations. Now let us now proceed with methods of preparation of phenols. Now let me discuss some of the important methods of preparation of phenols. One of the most important preparation where large scale production of phenols is usually achieved by subjecting coal tar to the fractional distillation. Whenever coal tar is subjected for fractional distillation, it gives mixture of organic compounds. Compounds such as phenols, chrysols, and benzene, they are obtained by purifying the fractions which are obtained from the coal tar. Phenol can be obtained even by fusing sodium benzene sulfonate with sodium hydroxide. Benzene ring with SO3Na group is known as sodium benzene sulfonate. So when this sodium benzene sulfonate is fused with sodium hydroxide, this process is known as alkali fusion. So upon alkali fusion, so this SO3Na group will be replaced by ONA. So that is how we will be getting sodium phenoxide compound. Now this sodium phenoxide, when it is treated with hydrochloric acid, so here sodium ions will be replaced by H plus ions which are present in the hydrochloric acid. So that is how finally we get phenol as the product. The next important method is one of the laboratory method which is known as Doe process. So in this, chlorobenzene is treated with sodium hydroxide at 360 degrees. So in this reaction, sodium hydroxide dissociates to give protons and ONA minus ions. So this ONA minus ions, these are nucleophilic in nature. and they will be replacing chloride ions which are also nucleophilic in nature. That means ONA minus ion will be replacing Cl minus ions. So it is a kind of nucleophilic substitution reaction. So as a result of which we will be getting sodium phenoxide as the product. Now when this sodium phenoxide is treated with mineral acids such as hydrochloric acid, there will be formation of phenol. So here again sodium ions will be exchanged for protons which are present in hydrochloric acid, and that is how we get phenol as the product. Phenols can be obtained even by the hydrolysis of aryl disonium salts. So aryl disonium salt, when we subject for hydrolysis, so the water molecule will be dissociated to give protons and hydroxyl ions. So these hydroxyl ions will be taking the position of disonium group, and that is how finally we get phenols. So in this reaction, we will get these H plus ions as one of the byproduct, and the disonium group will be removed in the form of nitrogen gas. So there will be liberation of nitrogen gas in this particular reaction. So this is known as hydrolysis of disonium salts. By this way, even by the hydrolysis of disonium salts also, we can obtain phenol. So dear students, I hope now this particular topic, that is methods of phenols, is crystal clear to you. Now out of the methods which I have given, at least try to learn at least two methods, okay? Whatever the methods that you feel very easy, you can learn at least those two methods, okay? So minimum two methods, okay? So maximum if you can learn, that is fine. But otherwise at least two methods you'll learn, okay? Now if you have any doubts till now, whatever the topic that I have taken, if you have any doubts, you can keep in the chat. Alternatively, you can join in that WhatsApp group also. The link for the WhatsApp group will be provided in the description of this particular video if you're watching the live session, or if you're watching the replay of this particular session also, it will be available in the description. So anytime you can join in that WhatsApp group and you can post your doubts. Okay, you can ask your doubts or clarify and get the support from me. Now, the next most important topic is reactions of phenols. Okay, now let us consider a few important reactions of phenols. The reactivity of any compound, it depends on its structure. That means the type of atoms and also the type of bonds present. If you look at the structure of phenol, it consists of benzene ring system with hydroxyl functionality. So due to the presence of hydroxyl functionality and this benzene ring system, it will undergo its own characteristic reactions. Now let us first have a glance of list of reactions that phenols can undergo due to its structure. Phenols are acidic in nature. So in the presence of aqueous alkalis, phenols can form corresponding salts. So due to the acidic property of the phenols, they will undergo salt formation reactions. The functional group present in phenols is hydroxyl group. So due to the presence of hydroxyl groups, it will undergo two reactions which are mainly meant for the hydroxyl group. So it will undergo esterification reaction and also it will undergo etherification reaction. Now the other structural feature left over in phenol structure is the aromatic ring system. So due to the presence of aromatic ring system, it will undergo reactions which are just similar to that of benzene. So due to the presence of this benzene ring system in the structure of phenol, phenols are considered to be aromatic in nature. And as I mentioned in the earlier module, all the aromatic hydrocarbons, they will undergo electrophilic substitution reactions. Hence, phenols also undergo aromatic electrophilic substitution reactions similar to that of benzene. A few examples are nitration, halogenation, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation reactions. Now, let me discuss about all these reactions one by one. Phenols having ability to lose protons, due to which phenols are having acidic property. As phenols are considered as acids, they react with base and they give corresponding salts. And thus, phenols will undergo salt formation reactions due to its acidic property. Phenols are acidic in nature and sodium hydroxide is a base. And that is how whenever reaction occurs between phenols with sodium hydroxide, acid-base reaction occurs, and as a result of which there will be formation of corresponding salt which is known as sodium phenoxide. Along with there will be formation of water as byproduct. The resulting salt is water soluble in nature. This salt formation reaction is a reversible reaction. Once salt forms, it may undergo reversible reaction whenever it interacts with mineral acids such as hydrochloric acid or sulfuric acid, and thus it will revert back to phenols. Phenols undergo esterification reaction due to the presence of hydroxyl group. So phenol, when it reacts with acyl chloride such as benzoyl chloride in the presence of sodium hydroxide, there will be formation of phenyl benzoate as the product. So this is the structure of phenol is written here, and this is the structure of benzoyl chloride. So C6H5COCl is known as benzoyl chloride. So these two molecules react in the presence of sodium hydroxide. So you can consider that hydrogen from phenols and chloride group from benzyl chloride will be removed in this particular reaction. So the resulting product is written by considering benzyl chloride structure first. So first write the benzene ring system of the benzyl chloride, then CO group, then this group, carbonyl group of benzyl chloride will be attached to the oxygen of phenol after reaction. So that oxygen along with the benzene ring system. So this part is obtained from phenol, while this part, okay, that is benzene ring C6H5 with CO group is obtained from the benzyl chloride. So this is how benzyl group will be attached to the phenoxide group, and that is how we get phenyl benzoate as the product. Phenyl benzoate is an ester because it consists of COO group. So this COO group is an esteric group. Thus, phenols upon reaction with acyl chloride such as benzyl chloride, there will be formation of corresponding esters. Phenols also undergo etherification reaction, that is Williamson synthesis, due to the presence of hydroxyl group in its structure. So phenols, when they are treated with alkyl halides in the presence of aqueous alkali such as sodium hydroxide, and upon heating this reaction mixture, there will be formation of corresponding ethers. So this AROR is nothing but ether. So let us consider an example. So here I have taken ethyl iodide as an example for alkyl halide. So when phenol reacts with ethyl iodide in the presence of sodium hydroxide upon heating, there will be formation of ethyl phenyl ether as the product. So in this reaction also, hydrogen from phenol and iodine from ethyl iodide will be removed during the reaction. And that is how ethyl group will be transferred to the oxygen of the phenol. So this particular structure, C6H5O part, is obtained from phenol structure, and this is the ethyl group which is obtained from the ethyl iodide. So this is how ethers will be formed due to the reaction between phenols with alkyl halides in the presence of aqueous alkali. This reaction is known as Williamson synthesis. So due to the presence of hydroxyl group, phenols, they undergo esterification reaction as well as etherification reaction, and they give corresponding esters and ethers as the products. Coming to the other type of reactions, phenols also contains aromatic ring system, similar to that of benzene. So due to the presence of this benzene ring system, they will undergo ring substitution reaction. That means the reaction occurs on the aromatic ring system. So they are nothing but electrophilic substitution reactions. The mechanism involved in the aromatic electrophilic substitution reactions was already discussed under chemistry of benzene. So for the mechanism, you can refer that particular module. Phenol is an example for the monosubstituted benzene. That is, it already consists of hydroxyl group. So when electrophile attacks on this monosubstituted benzene, it can attack at ortho position, or it can attack at meta position, or it can even attack at para position. Accordingly, there will be formation of ortho, para and meta isomers. But as I have discussed under effect of substituents on reactions of monosubstituted benzene in the earlier unit, so here the group which is already present on the benzene ring system is important. The group which is already present on the benzene ring system is hydroxyl group, and coming to the nature of the group, it is an electron donating group. And whenever electron donating groups such as hydroxyl group or amino groups are present, they will activate the ring system, and also they will orient the next incoming electrophile onto the ortho position and para position predominantly, because hydroxyl group is a ortho para director. So these details I have already discussed under previous module. You can refer to that particular course video. So whenever phenol is subjected for electrophilic substitution reaction, there will be formation of predominant yields of corresponding ortho isomer and para isomer. And coming to the examples of reactions, they are similar to that of electrophilic substitution reactions of benzene, which I discussed in earlier module. So some examples are nitration, sulfonation, halogenation, Friedel-Crafts acylation, and Friedel-Crafts alkylation. So here I am giving only two model examples for this reaction. So here nitration and sulfonation reactions are given. So phenol, when it is treated with dilute nitric acid at 20 degrees, there will be formation of corresponding orthonitrophenol derivative and paranitrophenol derivative. So first write the structure of phenol. Then, because hydroxyl group is an ortho-para directory group, here during nitration there will be generation of nitronium ion. So NO2 plus group will be liberated. So this group now attacks at either ortho position or para position, because in ortho and para attacks, the resulting carbocation is highly stable. So attach nitro group at ortho position and para position. So that is how there will be formation of ortho nitro and para nitro phenol derivatives. Now coming to the sulfonation reaction, phenol upon heating with concentrated sulfuric acid, there will be formation of corresponding orthophenol and paraphenol sulfonic acid derivatives. So here also write the structure of phenol first. So this is the structure of phenol, and upon sulfonation there will be attachment of SO3H group at ortho position and para position. And thus there will be formation of orthophenol sulfonic acid and paraphenol sulfonic acid. as product in case of sulfonation of phenols. So this is how reactivity of any compound, it depends on its structural feature. Because phenols are acidic in nature, they will undergo salt formation. And due to the presence of hydroxyl group, it will undergo esterification and etherification reactions. And due to the presence of aromatic ring system, it will undergo electrophilic substitution reactions, which are similar to that of benzene. So these are few important reactions of phenols. So again, students, in the reactions of phenols also, there are several types are there. The most important reactions only I have given here, okay? Out of these reactions, at least try to learn 2 reactions, okay? Like as you know, phenols are acidic in nature. The acidity of phenols often comes in the final examination also. So based on its acidic property, it has the ability to form salt formation. So you can stick to that particular reaction, the first reaction, okay? And phenols are also having aromatic ring system, similar to that of benzene, okay? Or phenol in fact is an example for monosubstituted benzene. So that is why it will also undergo reaction similar to benzene. So the ring substitution reaction. So at least these 2 reactions you can remember and you can prepare with the same and you can give the same reactions when it comes to the examinations. So instead of skipping the whole question, okay, instead of leaving the entire question, it is better you stick to simple reactions, okay, according to your convenience. Now again, if you have any doubts in the reactions of phenols also, you can post in the chat. Now let us move to the next important topic, that is dimer-dimer reactions of phenols. So under reactions of phenols, if they don't ask specifically also, you can include this dimer-dimer reaction also. So let me quickly share my screen. Whenever phenol is heated along with aqueous sodium hydroxide and chloroform, an aldehyde group will be generated and this group will be attached ortho to the phenolic hydroxyl group, and that is how there will be formation of salicylaldehyde as the major product in this reaction. So this reaction is known as dimer-dimer reactions of phenols. Now let us consider its mechanism. So in the first step, chloroform reacts with aqueous alkali such as either sodium hydroxide or potassium hydroxide. So from these alkali, hydroxyl groups will be reacting with chloroform. Because hydroxyl ions are basic in nature, they will try to always abstract protons. So they will abstract proton, that is hydrogen, from the chloroform. And that is how they will be making water. So OH minus, it reacts with H plus and thus there will be formation of water molecule as one of the product. Now in this reaction, when deprotonation occurs, that is when hydrogen is removed from chloroform, so the molecule will be retained with CCl3 unit. Because hydrogen is lost in the form of proton, the electron pair which is shared with carbon will be retained along with carbon. So that is how there will be formation of CCl3. Because it is having excess pair of electrons, it bears negative charge. Now the formed anion CCl3 minus ion, it dissociates into chloride ion and CCl2. So this CCl2 is known as dichlorocarbene, which acts as electrophilic reagent in this particular reaction. Dichlorocarbene consists of an electron deficient carbon. There will be 2 pairs of electrons from CCl bonds which are present in dichlorocarbene and a pair of electrons which are coming from the deprotonation in the first step. Okay, so overall, if you look at the electronic configuration, there are only 6 sets of electrons are available around the carbon. And it is lacking a pair of electrons to meet with the octet configuration. As you are aware, octet configuration is stable configuration. Thus, the carbon in dichlorocarbene is considered to be electron deficient, and it is because of that reason dichlorocarbene is considered as electrophile. As phenols usually undergo aromatic electrophilic substitution reactions, the formed dichlorocarbene acts as electrophile and it attacks onto the phenol ring system on the ortho position in the next step. Because phenolic hydroxyl group is orthopara directing group. By the action of phenol with aqueous sodium hydroxide, there will be formation of phenoxide. So the formed dichlorocarbene reacts with phenoxide ion. When dichlorocarbene attacks on aromatic ring system, because hydroxyl group is an activating group and also it is an orthopara directing group, this dichlorocarbene attacks on the ortho position on this aromatic ring system. So while attacking dichlorocarbene, it utilizes one of the pi bond which is available at the ortho position. By utilizing this pair of electrons, CCl2 group will make a bond with the aromatic carbon. Because it is getting excess pair of electrons from the aromatic ring system, there will be generation of negative charge on the CCl2 group. When we transfer this pi bond, there will be deficient of electrons at first position. To compensate that, the electrons which are present on the phenoxide ion will be transferred. So that is how there will be formation of a double bond in the intermediate. Now in the next step, proton transfer occurs. because CCl2 group is bearing negative charge and in the surrounding there is availability of protons. So these protons will be lost from the second position and they will be immediately taken up by the carbon of the CCl2 group, and that is how there will be formation of CHCl2 group ortho to that of the phenolic hydroxyl group on the benzene ring system. While deprotonation, this bonded pair of electrons will be again transferred in the form of double bond. That is how the aromatic ring system gets back its third pi bond. In that case, the first carbon becomes pentavalent. To compensate that, the doubly bonded electrons are again transferred back onto the oxygen in the form of negative charge. That means here the bond between carbon and hydrogen will be transferred in the form of double bond. As soon as double bond is formed at this particular position, immediately the doubly bonded electrons will move onto the oxygen in the form of lone pair of electrons, and thus again oxygen gets back negative charge. And that is how there will be formation of a transition state intermediate. So this intermediate is highly unstable, and that is the reason immediately CHCl2 group will be converted to an aldehyde group in the immediate step. Now, when this ultimate intermediate is subjected for mineral acids such as hydrochloric acid or sulfuric acid, immediately protons will be taken up by the phenoxide group, and thus there will be formation of salicyl aldehyde as the product. So this is how upon reaction of phenols with chloroform in the presence of aqueous alkali, the aldehyde group will be transferred onto the ortho position on the phenolic ring system, and that is how finally we get salicyl aldehyde as the product. So this reaction is known as Reimer-Teimer reactions of phenols. This reaction is one of the most important question in your internal examination as well as external examination. First, learn the definition and single line reaction, then try to learn the mechanism involved in it. Now that you have learned what is Reimer-Teimer reaction and its mechanism, so if you have any doubts in this reaction, you can share in the chart, students, because it is one of the most important question. Okay, so if this is clear to you, now next we will move to the next important topic, that is STT of phenols. Okay, so most of the previous question papers you can find this particular question. Okay, that is STT of phenols and the effect of substituents, that is electron donating as well as electron withdrawing groups on the STT of phenols. Now let us proceed with this. So meanwhile, if you have any doubts till now, whatever the topics that I have taken, you can post in the chat. The ability of compounds to lose protons is the measure of STT. Phenols, they lose protons whenever they are treated with aqueous hydroxides. That is, whenever they are treated with either sodium hydroxide or potassium hydroxide, the hydrogen of phenol will be abstracted by the hydroxide group of the aqueous alkalis, and thus OH minus ions reacts with H plus, and thus there will be formation of water molecule as the byproducts. Upon losing this proton by the action of base, phenol gets converted to corresponding phenoxide ion. So here, the STT of phenols is measured not only in terms of their ability to lose their protons in the presence of aqueous alkalis, but also it depends on the stability of the resulting phenoxide ion. But this reaction is a reversible reaction. So in the presence of mineral acids such as hydrochloric acid or sulfuric acid, the formed phenoxide ions, they will give back phenol. Not only phenols, even the water molecule, alcohols and carboxylic acids are having ability to lose protons. So water upon dissociation, it gives protons and hydroxyl ions. Whereas alcohols also in the presence of aqueous alkali, so this hydrogen of alcohol will be abstracted by the action of alkali, and that is how there will be formation of corresponding alkoxide ion. Even carboxylic acids also, they react with aqueous alkali, and upon abstraction of the proton of the carboxylic acid by the action of alkali, there will be formation of carboxylate ion. So in all these reactions, if you see, there will be liberation of protons. So either there will be liberation of protons is shown, or the liberated protons, they will complex with hydroxyl group and they will form water molecule. So the compound which gives protons upon dissociation is considered to be an acid. As per this definition of acids, all these are considered to be acidic in nature. But among all these compounds, the extent of acidity, it will vary. So among all these compounds, carboxylic acids are having greater acidity when compared with phenols, alcohols, and then water. Water is having least acidity among these compounds. For the current discussion, let us compare the acidity of phenols with alcohols. Alcohols, when they treated with aqueous alkalis, so this hydrogen will be abstracted by the action of base, and thus it results in the formation of corresponding alkoxide ion. So in case of alcohols, the resulting alkoxide ion has only one structure. When it comes to phenols, even phenols in the presence of aqueous alkali, they undergo deprotonation. That means there will be liberation of protons, and upon abstraction of protons, there will be formation of corresponding phenoxide ion. But in case of phenol, the resulting phenoxide ion is stable by resonance phenomena. So let us look into the resonance phenomena in case of phenol and the resulting phenoxide ion. Because both of these compounds are bearing the aromatic ring system, that is benzene ring system. As we have discussed in the earlier unit, benzene has two kcl structures. Now let us write the kcl structures for benzene ring. So these are the two resonance structures written for phenol by considering the kcl structure for the benzene ring system. So this is one kcl structure and this is the another kcl structure where both are having hydroxyl group. So these are the two resonance structures for the phenol. Now coming to the resulting phenoxide ion also, the kcl structures were shown for the aromatic ring system, and that is how this is one resonance structure and this is the second resonance structure for the resulting phenoxide ion. So in case of phenols, both phenol and the phenoxide ions are stable by resonance phenomena. So in case of phenols, the resulting phenoxide ion is stable by resonance phenomena. That means the resulting phenoxide ion has more than one structure. So that is what is known as resonance. Because of this reason, the phenoxide ion is more stable when compared with alkoxide. Greater the stability of the resulting ion, greater will be the acidity of the molecules. Hence, phenols are more acidic when compared with alcohols. Both phenol as well as phenoxide ion, as they are having aromatic ring system, they can be represented each with two resonance structures. That means the starting compound phenol is having two resonance structures and also the resulting phenoxide ion is also having two resonance structures. It indicates that the stability of the formed product is same as that of the starting compound. Usually any compound, it undergoes reaction to attain the stability. But in case of phenols, by considering these two kcl structures, we can say that the resulting compound is as stable as that of the starting compound, that is phenol. This resonance phenomena, it stabilizes both the molecule and the ion to the same extent. So this gives an indication that the potential energy of the resulting phenoxide ion is same as that of the potential energy of the starting compound, that is phenol. When there is no potential energy difference between the resulting phenoxide ion with that of the phenol, then the stability of phenoxide ion is just considered to be same as that of the alkoxide ion. That means the acidity of the phenols and alcohols would be similar, right? From the acidity constant, we can easily make out that phenols are having greater acidity when compared with alcohols. So the greater stability of the phenoxide ion when compared with alkoxide ion can be explained with the help of some more additional resonance structures which are possible in case of phenoxide ion. So additional resonance structures are possible both for phenol as well as the phenoxide ion. So these are the three more resonance structures possible for phenol, and these are the three additional resonance structures possible for the resulting phenoxide ion. If you look at the resonance structures of phenol, each resonance structure, it consists of positively charged center and the negatively charged center. In that case, the molecule requires greater energy to separate the opposite charges. In the phenol resonance structures, we can say that the energy of phenol is high due to the existence of opposite charges, that is positive and negative charges in the same molecule. This causes greater utilization of the energy to separate the charges. So it is because of that reason, even the same number of resonance structures are possible both for phenol and phenoxide, the stability of phenol is less. So in case of phenoxide ion, so each of these structures are having only negative charge. The negative charge is localized at two ortho positions and para position. So the extent of energy needed for this molecule is relatively less when compared with phenol. Lesser the energy needed, greater is the stabilization. So it is because of that reason, even though both phenol and phenoxide ions are having same number of resonance structures, yet the resulting phenoxide ion is more stable and the resonance phenomena is more prominent in case of phenoxide ion. It is because of this reason, phenols undergo easily deprotonation in the presence of aqueous alkali and they readily give corresponding phenoxide ion because it is stabilized by resonance phenomena. Hence, they are more acidic when compared with alcohols. Now, let us consider the effect of various substituents on the acidity of phenols. So, these substituents, as you are aware, can be divided into two categories, that is electron withdrawing groups as well as electron releasing groups. Phenols having various substituents, when they are subjected for alkali treatment, they also forms corresponding phenoxide ions upon deprotonation. Now, let us consider the first example where G is a group which is an electron withdrawing in nature. For example, halogen, nitro group and carboxylic acid groups. So these are few examples for the electron withdrawing groups. When a phenol is having electron withdrawing group, the resulting phenoxide ion is highly stable. Let us see what is the reason. So as a result of deprotonation, the compound will be giving corresponding phenoxide ion. When electron withdrawing groups are present on this ring system, the nature of electron withdrawing groups is that they will cause withdrawing of the electrons. That means they will try to withdraw the electrons from the aromatic ring system, which is already having the negative charge. So this causes dispersal of the negative charge on the ring system. So this dispersal of the negative charge causes stabilization of the resulting ion. Thus, the resulting phenols are more acidic in nature. That means presence of electron withdrawing groups makes the molecule more acidic. On the other hand, whenever electron donating groups are present, even those molecules, they give corresponding phenoxide ion, but in case of the resulting ion, it is destabilized. Amino group, hydroxyl group and methyl groups are the examples for the electron donating groups. Phenoxide ion is already holding the negative charge. Now, due to the presence of electron releasing groups are nothing but electron donating groups. That means they will donate their electrons towards the ring system, which is already having the negative charge because it is a phenoxide ion. So, this causes intensification of the negative charge. Already the ion is having negative charge. Further, due to the presence of electron releasing groups, the negative charge will be increased. So, this causes destabilization of the resulting ions, and thus whenever electron releasing groups are present on the aromatic ring system, the resulting phenols are less acidic in nature because the stability of the resulting phenoxide ion is less. So here the thumb rule when it comes to the effect of substituents on the acidity of phenols is whenever electron withdrawing groups are present, they increases the acidity of phenols, while whenever electron releasing groups or electron donating groups are present, they decreases the acidity. So the acidity of phenols and the effect of substance on the acidity of phenols is one of the most important topics for your internal examinations as well as external examinations. So this concept is just similar to the acidity of carboxylic acids, aliphatic carboxylic acids, which you learned in the previous semesters. So whenever it comes to the acidity of carboxylic acids, aliphatic or aromatic carboxylic acids, acidity of phenols, it will be discussed under similar lines. Okay. So the first important criteria is why a compound is acidic. That is, these molecules are having ability to lose protons. So that causes acidity to the molecules. And the second important aspect is the resulting ion, whether it may be the carboxylate ion in case of carboxylic acids or the phenoxide ion in case of phenols, should be stable. Then only the molecules will be having ability to readily lose the protons, and then only they are considered as the acidic compounds. So which of these phenol molecules, okay, can readily lose the proton, that depends on the formed phenoxide ion stability. So in case of phenols which are having the electron withdrawing groups, the formed phenoxide ion is readily stabilized because of the dispersal of the negative charge due to the presence of electron withdrawing functionalities such as nitro group, halogen or carboxylic acid moiety. Now, when it comes to the electron releasing groups such as methyl group, amino or hydroxyl groups are present, then the resulting phenoxide ion is destabilized because due to the intensification of the negative charge, and thus they are less acidic in nature. So I will stop today's session here, students. So I hope this acidity of phenols is clear to you. Now let me give quick pointers, that is key pointers or key takeaways when it comes to the chemistry of phenols. That means what exactly you have to learn at least to get B grade. Okay, so let us aim for B grade. As I mentioned repeatedly in all the live sessions, it depends on your goal, whether your goal is to clear the examinations, okay, POC-II subject, or to get O grade, A grade or B grade. Okay, accordingly you have to proceed with the preparation. Okay, so yeah, accordingly you have to plan for the preparation. Okay. So based on today's session, I'm just giving few important key takeaways. So first, to learn at least what is the definition and structure. For example, if you could not understand anything in the phenols, okay, could not prepare, you left this whole topic, but still you came and you have to attempt this particular question to get at least pass mark. So in that case, at least try to learn the definition and that phenol structure. Okay, and wherever phenol question comes, okay, whatever the question comes from phenol chapter, write that at least. You will get 1 mark. Okay, so in that way also at least you will get pass mark. And the next important one is I have discussed about methods of preparation. So out of all the methods given by me or in your textbooks, at least you learn 2 important methods, whatever you feel easy. Okay. And under reactions also, several reactions I have discussed, and you will find several reactions in your textbooks, but at least 2 reactions try to learn. As I mentioned earlier, at least a salt formation and ring substitution. Ring substitution reactions are not new to you because you have already learned this particular topic in the benzene. Okay. So both benzene So both benzene and phenol, they consist of aromatic ring system. Okay, because you learned already 5 reactions, nitration, sulfonation, and all those reactions for benzene. So the same, at least 1 or 2 reactions you can give for phenol also. Okay, only thing is you are not aware if you are unsure about the point of attack. For example, as I explained, hydroxyl group is an activating group. So it is an ortho para directing group. If you are unsure what type of product you have to write, whether ortho, para or meta, at least you can give like this, like first write the phenol structure in the product, and if you are unsure about the substituent, okay, then from the center you make a line and keep Y. Whether it is nitration, if it is a nitration, keep here NO2 group. If it is sulfonation, keep SO3H group. If it is chlorination, keep Cl group. Like that. From center, make a line and you write that group. Okay, if you are unsure about the substitution. So like that also you can write. And if it is nitro, you can just mention it as nitrophenol as the compound name. So like that, a general name or a specific name also you can give by omitting the position of the nitro group, whether it is present at ortho, meta or para position. If you are unsure, you can write just like this also. Now, the next important one is Reimer-Timer reaction. Okay. So if you feel mechanism difficult, because you know that it is one of the must question, it is a definite question. So at least learn what is the meaning of, that means what happens in the Reimer-Timer reaction, definition means. Okay. And what is that single line reaction? Okay. So that means phenol reacts with chloroform in the presence of aqueous alkali and it gives aldehyde as the product. So that is the definition. And what is that single line reaction? At least learn that. Now, anyway, if you learn Reimer-Timer reaction, you can include this also under reactions of phenols if that question comes. Okay. And the next very, very important topic is acidity of phenols. Okay. So here you can, I have already discussed what are the key points under acidity. So why phenols are acidic in nature and that single line reaction is there. No, you show that. Okay. And you just mention that stability of formed phenoxide ion is important. Okay. And you just write the 2 reactions at the end, whatever I have shown under acidity, effect of the groups. Okay. That is electron donating group with the drawing group. Okay. So at least if you learn by omitting all the resonance structures, if you learn up to this part also, at least you will get 3 marks or 3.5 marks out of 5 marks if you get it as a 5 marks question. Okay. So that is about acidity of phenols. Okay. And the other important topic which I have not discussed is structure and uses of phenols. Okay. So 4 phenolic compound structures were given in your syllabus. So at least learn those 4 structures and at least 1 or 2 uses for each structure, because repeatedly you will be finding this particular question in the final question paper. So that is also important. Okay. So these are few important pointers when it comes to the chemistry of phenols. So under each topic, learn just what is what. Okay. So what are phenols? Example. What is Reimer-Timer reaction? Example. So like that, very simply you write also. So prepare, no need to afraid about this particular topic, students. Just prepare very briefly. So if you can prepare such that if you write all these topics of phenols on one paper, it should come only single side. Okay. That means it should accommodate in a page. Okay. So this is single side of the paper is known as page, 1 page. Okay. So like that. Phenols, 1 page. Okay, aromatic carboxylic acid, another page. And similarly, the aromatic amines, another page. Just make all the concepts, prepare all the concepts very briefly. Okay, so that it will come only 1 page. Okay, so if you have 10 topics in whole POC-II subject, that means you will be preparing only 10 pages of material and you will stick to that material and learn it, practice it very well such that you will write, when it comes to the examination, you will write such that there will not be any single mistake in your paper. Okay, so learn it very briefly, but write it when you are presenting in the examination, write it without any mistake. You will definitely score up to B grade. If you write very briefly, but without any mistakes with good handwriting, definitely you can aim up to B grade. Okay, that means you will not only pass POC-II exam, but you will also get B grade. Okay, now to get A grade and O grade, of course, all the mechanisms you have to be thorough, but you have to present without any mistakes. Okay, so that's all for today, students. I hope now this phenols topic is clear to you. Okay, so similar to phenols, prepare. I will be taking other topics also up to 12th January. As you are aware, these sessions will continue. Okay, I will take other topics also, but whatever I am teaching here, from that, just take the gist. Okay, so I'm giving explanation to make you understand the concept sometimes very deeply, but take whatever is very necessary. Okay, prepare with that and produce it in the examination without any mistakes. Okay, so definitely you will rock these POC-II exams for sure. Okay, so that's all for today. In tomorrow's class, I'll be taking chemistry of aromatic carboxylic acids. Okay, now let us meet in tomorrow's session. Take care.